Hello students, so today we are going to discuss about fundamental theorem of arithmetic. This is a theorem explaining a very important feature about the positive integers, and to be very precise, it's all about primes and composite numbers. So we shall start with discussing the basics of the primes and composite numbers, that is the examples, the definitions and the relationship between primes and composite numbers. So let's start with prime numbers. Till now, we know primes are the numbers which have exactly two factors, that is 1 and the number itself. It means the numbers other than 1 and the given number cannot divide the given number exactly. It's a very common thing. We know every number is exactly divisible by 1 and itself, and the number which is only exactly divisible by 1 and itself are called prime numbers. Let's now understand these numbers from a different aspect. Now we can name those numbers primes which cannot be divided into groups of equal numbers greater than 1. Means say you have some chocolate and you want to distribute these among some children, and the condition is you have to distribute these to more than one child, and each child will get equal number of chocolates, and that too more than one chocolate. Okay, any number of chocolates can be distributed among number of children by giving them one chocolate to each, but the condition is you have to give more than one chocolate and each child should get equal number of chocolate. So say you have 3 chocolates. If you want to distribute this more than one child, that is to 2 children, you have to give 2 chocolate to one and 1 chocolate to another one. So everyone doesn't get equal number of chocolate. So 3 cannot be divided into groups of equal numbers. So 3 is a prime number. Similarly 5, if you want to distribute 5 equally into groups, it cannot be, because 5 can be divided as 2 into 2 groups. There are no equal chocolates. Or if you want to distribute 5 in other ways like 2 to 1, also one child is getting 1 chocolate, so 5 is also a prime number. Similarly 7, it cannot be divided. If you want to divide these into groups, it can be 3, 4, 11 can be 4, 7 or 3, 3, 3, 2 or 5, 6. There will be no possible ways to divide 11 into some groups of equal numbers and that number is greater than 1. It can never happen. So these type of numbers are called prime numbers. Now I hope you have a clear idea about the prime numbers. So prime numbers are the numbers which cannot be divided into groups of equal numbers. Okay. On the other hand, composite numbers are the numbers which can be divided into groups of equal numbers more than one, that too 2 or in more than 2 ways. For example, you have 8 chocolates. So it can be divided into 2 groups of 4 and 4. It can also be divided into 4 groups of 2. Similarly, if you have 6, you can divide 6 into 2 groups such as 3, 3. You can also divide this into 3 groups of 2, 2, 2. Similarly, if you have 10, it can be divided into 2 groups of 5 and 5. It can also be divided into 5 groups of 2, 2, 2, 2, 2. Similarly, if you have 12, it can be divided into groups in many ways, such as 6, 6 into 2 groups, 3, 3, 3, 3 into 4 groups, 4, 4, 4 into 3 groups, 2, 2, 2, 2, 2, 2 into 6 groups. Alternately, you can also say composite numbers are the numbers which have more than 2 factors. Obviously 1 and itself are the universal factor. Other than them, there would be at least 1 or more than 1 numbers which can divide the given number exactly. Now I hope your memory about the primes and composites would have been refreshed. So now let's move to the next step. As we know, we always try to find out a pattern among the numbers so that we can easily identify and list them and arrange them in a proper way. Such as for even numbers, we know that the numbers which has 0, 2, 4, 6, 8 are the unit place, those are called even numbers, and we can easily identify the numbers which are even, and we can also list and arrange them in a proper manner. Similarly, odds are the numbers which are not even or which have 1, 3, 5, 7, 9 are the unit place. So similarly, to find out or to identify which are the primes and composites, we should always try to find a pattern among them. So for this, all the mathematicians from ancient time are trying to find out a pattern, but sadly no one has succeeded till today. But luckily in 300 BCE, this mathematician Euclid of Alexandria was able to find out a relationship between the primes and composites. So let's find out what did he discover. For this we need to list the primes and composite numbers up to 20 separately. So let's move to this. Now as you can see, I have all the numbers here up to 20. So let's quickly first classify these into primes and composites. The first number is 1, and we know 1 is neither prime nor composite, so we will take this away. Now 2, yes, it is prime because 2 is only divisible by 1 and 2. Similarly 3 is also prime. 4, it has two factors, 1 and 4. With this it has also another factor, that is 2. 5, it is a prime number. 6, it is divisible by 2, 3 also, so it is composite. 7, it is prime because it has only two factors, 1 and 7. 8, it has 1, 2, 4 and 8, 4 factors, so it is. Don't be confused about 9, it is an odd number but it is composite because it is also divisible by 3. 10, it is obviously a composite one. 11, it's a prime. 12, it's composite. 13 prime. 14 composite. All the even numbers ultimately are the composite ones because 2 is a factor of every even number. Some of the odd numbers are primes, but some of the odd numbers are also composite. 16, it is composite. 17, it is prime. 18, composite. 19, prime. 20, composite. So as you can see, I have organize these numbers into prime and composites. Now let's see what did Euclid discover. Euclid discovered that every of these composite numbers can be written by multiplying one or more than one of these primes taken to a specific number of times. For example, here 4, it can be written as 2 times 2, and 2 is a prime number, here you can see. Similarly, 6 can be written as 2 times 3. 2 and 3 both are primes. Similarly, 8 can be written as 2 times 2 times 2. 9 can be written as 3 times 3. 10 can be written 2 times 5. 12 can be written 2 times 3. You can see 14, it can be written as 2 times 7. 15, it can be written as 3 times 5. Here 3 and 5 are primes. Similarly, 16 can be written as 2 times 2 times 2 times 2. 18, 3 times 3, 9 times 2. Similarly, 20, 2 times 5, 10, again 2 times. So we'll get 20, 2 times 5 times 2. So as you can see, each of these composite number can be written by using prime ones. This is why, as these numbers are composed of these prime numbers, that's why these are called composite numbers. And on the other hand, prime numbers are the building blocks of the composite numbers. Means by multiplying any of the prime numbers to a specific number of times, we can get a composite numbers. As these plays the prominent role in building the composite numbers, that's why these are called primes, means the important ones. I hope now you would have a clear idea why these are called primes and composites. Now let's analyze this situation in a reverse manner. Here we got these composite numbers are composed of sum of the prime numbers taken or multiplied to a specific number of times. Alternately, we can say any prime numbers can be taken and multiplied together to a specific number of times to get a composite number. Easy, I just told this in a reverse manner that if we multiply any of the prime numbers, we will get a composite number. And to be very precise, you will get a unique composite number. Means if you multiply 3 by 5, then you will get only 15, not any other composite numbers. That means no two composite numbers share the same combination of primes. Yes, the order may change, means here you got 3 cross 5, 15, Also you can get 5 cross 3, 15. The order may be changed, but the combination is unique. Means here you have 1 5 1 3. Here also you have 1 3 and 1 5. The order may change, but if you take the same combination of primes by changing the orders in different manner, you will get the same composite numbers every time. Okay. So we got now every of the composite number can be written by multiplying the prime numbers to a specific number of times, and no two composite numbers share the same combination of primes. Exactly this is what we call fundamental theorem of arithmetic. Okay, so now let's see what the statement of this fundamental theorem of arithmetic says. This says every composite number can be expressed, every composite number can be expressed or factorized as a product of primes, and this factorization is unique apart from the order in which prime factors occur. Okay, so this says every composite number can be expressed or factorized as a product of primes, and this factorization is unique apart from the order in which prime factors occur. So let's take an example to understand this again clearly. So it says every composite number, say any composite number be 468. It's a composite number, clearly it can be seen that it is an even number as 8 is in the unit place, so it must be a composite number. So every composite number can be expressed or factorized. Factorized means expressed as a product of some numbers is called factorized. So it can be expressed as a product of prime. So let's see how can we write 468. So if I will do the factor tree that we had studied in class 7, if I first divide 468 by 2, I will get 2 2 is 4, 2 3 is 6, 2 4 is 8. So we got 2 and 234. Again 234 can be divided exactly by 2. So now we got 2 1 is 2, 2 1 is 2, 2 7 is 14, 117. We can divide it by 3. 3 3 is 9, 27, 3 9 is 27. Again 39 can be divided by 3. So we will get 13 3 is 39. Now at the end we got 13, which is a prime number. We cannot again divide 13 exactly by any other number. So 468 now can be written as, there are 2 times, so we can write it as 2 squared. Next multiplied, there are 2 3's, so 3 squared into one number last, it is 13. So 468 can be expressed as the product of primes. Here 2, 3 and 13, each of them are prime numbers. So up to this it's clear. Now it is written this factorization is unique. Okay, this factorization is unique means if you multiply 2 times, 3 2 times and 13 to them, then you will always get 468. It's very clear, because there are no other numbers we are changing, so we will not get any other composite number. If you multiply these 5 numbers, you will always get 468. So this factorization is unique apart from the order in which it occurs. Yes, unique, it is unique, but the order may change. Apart from the order, okay, the order may be changed. Means if I will first here 468, if I will first divide this by 3, I will get 3 1 ja 3, 16 3 5 ja 15, 3 6 ja 18. Now we will again divide it by 3, we will get 3 5 ja 15, 3 2 ja 6. Again let's divide it by 2, we will get 26. If we will divide 26 by 2, we will get 13. So here we got again 1 2 3's, 2 2's and 1 13 also. So it can now be written as 3 squared. Firstly we had got 3, so I wrote 3 first, then 2 times 2 squared and again 13. This same 468 was written here 2 squared times 3 squared times 13. Now it can be written as 3 squared times 2 squared times 13. Here 2 squared was at the first or the beginning, and here 2 squared is in the middle. Here 3 squared was in the middle, here 3 squared is in the beginning, and coincidentally 13 is at the end in both the cases. But here the order is changed. But if you see the combinations, here there are 2 2's, here also there are 2 2's, here there are 2 3's, here is also there are 2 3's, here there is 1 13, and here also 13 once multiplied. So the combination is unique always. Yes, the order may change among the prime factors. So this is what fundamental theorem of arithmetic says. Means it gives you nothing but another definition of composite number. Means whenever you are given to prove or check whether a given number is prime or composite, how can we check it? We will just factorize that, and if you are getting some prime numbers multiplied together to get the given number, then the given number is composite one. Okay, so now I can hope you have clearly understood fundamental theorem of arithmetic. Now let's solve one question from your textbook and we will complete this session. So there is a question in your exercise 1.2 and the number is 6. The question is something like this: explain why 7 into 11 into 13 plus 13 is a composite number. There are two numbers given. I am solving here only one. So here it is written why this given expression is a composite number. As we just studied here, every composite number can be expressed as the product of prime numbers. So let's see whether this can be written as the product of primes or not. At first let's see what is given in the question. It is given 7 multiplied by 11 multiplied by 13. Up to now that you can see 7, 11, 13, each of them are primes and they are also multiplied. So up to this is a composite number. But the problem arises here another 13 is added to it, not multiplied to it. If it would be multiplied, then no problem, we can clearly could say that this is a composite number. But now as there is a addition sign or plus sign, this creates problem that we can't say directly that it is a composite number. So now let's see how can we solve this. So at first what will you do? We will just try to eliminate this plus sign. So what we will do, we can see there are two terms, basically 7 into 11 into 13 is one term and 13 is another term. So we can take 13 common. So we will get 7 into 11 here left plus 1 whole into 13. I just took 13 common from both the terms. Now let's try to solve this bracket. We will get 7 into 11 77 plus 1 multiplied by 13. Next 77 plus 1, it is 78 multiplied by 13. Now we have succeeded in eliminating this plus sign. We got 78 multiplied by 13. But the problem here is now 78 is a composite number. But to prove this as a composite number, we need to get each factor of the final result to be prime. So next again let's factorize 78. Let's see what we are getting. If we factorize 78, if you divide it by 2, we will get 2 3 ja 6, 1 18, 2 9 ja 18, 39. it can be exactly divisible by 3. So 3 1 is 3, 3 3 is 13. Now 13 is a composite, sorry, 13 is a prime number. So now we got 78 can be written as 2 times 3 times 13. So now let's replace this in place of 78. So in place of 78 we can write 2 times 3 times 13, and again there was another 13 multiplied here. So now this original expression given to us was 7 into 11 into 13 plus 13, and the same expression is turned to be another expression such as 2 times 3 times 13 times 13, and here each of the numbers multiplied here is is prime number, and also there is no other sign except multiplication. So we can clearly say this is a composite number as some of the prime numbers are multiplied to a specific number of times here. So it is a composite number. Ultimately the original given number is also composite number. Okay, now I hope you can also solve the other one given in your question number 6. With this session ends here. Thank you.